He started this just 3 years after he started his career. So at a very young age, he founded this along with his brother and a couple of other friends. And they've been running this for the last 10 years now very successfully. And he's a very active community contributor. And he's one of the first TiDB certified engineer outside the pink cap in the world. So without further delay, I think we can go get started. Good luck. That'll work, I'll push.
Good afternoon, everyone. Today's topic, unleashing data at scale with TiDB. So how many of you heard about TiDB? Okay. So how many of you have worked with MySQL? Okay, I see a lot of hands. Looks like. So this is a small intro about me. Interested in open source technologies. I'm the PingCap certified DBA, and I'm also a co-founder of MyDBOps. So I have around a decade of experience with coming back to databases. So this is small about MyDBOps, what we have done in the last 5 years of timeline. Sorry, 7 years of timeline. So we have around 300 clients across the globe, and we have handled 3,000 plus servers with various use cases and various loads. And we are also a ISO PCI certified company. And recently we got a partnership with TiDB. Okay. So these are the services what we provide in MyDBOps. We have a targeted engagement like a consulting, wherein we have a scope, you drive through the project like a migration or things. And we also have a 24/7 managed database support. So these are the technologies what we support. So MySQL, Mongo, Postgres, and recently we added the TiDB and Cassandra, and also we are also exploring other distributed SQLs. So without further delays, let's jump on to the topic. So this is the agenda for today. So what is TiDB? I'll give an introduction about what TiDB is, what does it brings to the table, and what about this history and where it is being used. And I'll discuss about the architecture, how the architecture internally works, and the sharding feature. So TiDB brings in table with an native sharding, how the sharding works and how the data is being split among the nodes, how the fault tolerance is being handled, and the production readiness. So what are the things you should check with respect to the production readiness, and also the major use cases where it is being used, at what scale they are being used in TiDB. Excellent. So what is TiDB? So TiDB is an open source sharded database which is a drop-in replacement for MySQL, and it is wire compatible with MySQL 5.7. So for example, you have an application which is running with 5.7, you can directly change the connector to TiDB, and start work as it is like a MySQL. And it supports both transactional and analytical workload in the same. So this is a kind of HTAB. HTAB is nothing but an hybrid transaction analytical processing system. So let's see, it is also highly available and fault tolerant. So what are the bottlenecks? For example, you have your current system like running with MySQL. The single node bottlenecks comes into the picture. For example, you have a data which is scaling well. For example, till 1 TB MySQL can scale very well. When it goes beyond 1 TB, for example, you have a table which is more than 600 or 700 GB, altering a table might be very difficult, or overnight task activities, right? And also horizontal sharding is not available with respect to MySQL on the fly. That means there is no native sharding. You might need to use Vittis or other third-party solutions to get the sharding done and distribute your data, or else you might need to have an application level sharding. That means the application should be like intelligent enough to or shard aware to get your data. And so coming back to the architecture, so TiDB as a cluster has three major components. That is a TiDB cluster, that is a SQL layer. It manages the connection, your authentication, and those things. And next is the TiK, which is your storage layer. This storage layer is based upon RocksDB. We'll explain it in the later slide. And placement driver. This is the orchestrator, or we can call it as the brain of the cluster. Means it handles everything. That means it orchestrates what are the activities that is being done with the TiDB cluster. And the optionally, this is the TiFlash. This makes it as the analytical workload. So the TiFlash is based upon columnar storage. Next slide. So this is the architecture of TiDB. So each works as a decoupled one. For example, this is your application protocol, that means your connector, and TiDB sits and talks with your application. You can, this is your SQL layer. Basically this SQL layer talks to the storage cluster to two APIs, that is a distributedsql API and the KV API. KV API is nothing but an key value pair API. So whatever the queries or the writes which comes through the application is being changed as a key value pair, and this being sent to the storage layer for the writing. And when you give a select or the read query, the distributed SQL, right? So this gets some metadata information from the PD and collects the gets the information from the storage layer and traverse back to the application. So this is the architecture. We'll discuss in detail about what are the major functionalities of each of the layer. Next slide. So TiDB. So TiDB as a SQL interface, this interface is completely stateless. That means it does not store any of the data. So you can run as much as TiDB nodes you want. For example, you can integrate this along with your application layer so that it can talk to the storage layer directly. And what are the things it does is it handles your connection. So for example, you need to scale up your application with respect to the connections. You can increase the number of TiDB nodes, and parsing and compiling is done at this SQL layer. The first query, the layer of query you send, right? For example, you send a select, those queries are being parsed. For example, in MySQL you have a separate parser which is the optimizer. Here the parsing and compiling is done at the SQL layer, and the parsed one is sent to the storage layer via the distributedsql module, and from the distributedsql module it gets the required data and sends it back to the client. And this module also controls the online DDL execution. So DDL operations with respect to TiDB is online. It maintains a separate queue and also a history queue within the TiDB cluster, and it keeps tracks of the jobs to be run within the TiDB for the DDL activities. And garbage collection. So TiDB also supports MVCC, that is multi-version concurrency control, with the snapshot isolation. So when this snapshot isolation is being used, so you have a huge chunk of data being grown at the background. That means your older data, that is snapshot data. So those snapshot data will cleared by this GC activities, that means garbage collection activities. This is initiated by this SQL layer or the TiDB layer. And also catchy table. So this catchy table is a new feature in TiDB. That means the maximum size of the catchy table is 64 MB. For example, you have a config table that is being not changed. You can have this table as a catchy. That means this will be cached in your SQL layer, and whenever you use it, right, it will be available immediately. So the catchy table, what kind of data fits into the catchy table? For example, a config table or a data that does not change, like a static data you can use for the catchy table, and this feature is available from version 6.0. So next comes our transactional storage layer, that is a TiKV. So this is stateful. That means this minimum the TiKV node should be 3 nodes because to maintain the quorum. And this is persistent with RocksDB. The underlying storage is based upon the RocksDB. It is a LSM tree. It is highly optimized for writes. And also this also supports an distributed storage. That means the data within the TiDB is being segregated or chunked across all the nodes. We'll see in later slide how this chunking and the distribution works with respect to the TiDB. This TiDB, the entire distributed storage and transaction support is based upon the Google Spanner and F1 paper, and this provides a strong consistency. That means TiDB supports ACID compliance. So whatever the atomicity, consistency, every feature is available with the TiDB also, and it also has an inbuilt HA and coprocessor, right? This is a single TiKV node inside a cluster. Minimum you will be having a 3 nodes within the TiDB cluster. Each will have a coprocessor. The functionality of the coprocessor is to reduce the computational overhead as well as the network overhead of the SQL layer. For example, this TiKV will have a chunk of data. That means a partition of data. For instance, when a select star of a table, particular table comes, this TiKV node might have like a range of say 1 to 30 of it, and other node will have the remaining data. So what it does is it gets the data, and coprocessor will run the computing. For example, you do a count of star, the partial count of star is being done here by the coprocessor, and this result is being sent to the SQL layer, that is a TiDB layer, and TiDB collates and add them and send it to the client. So therein, by reducing this computation is being pushed to the TiKV layer, and also it reduces the network overhead of transferring the data from TiKV to the SQL layer. So next slide. So this is how the data is being distributed. Okay, so region is the smallest atomic unit within the cluster. So region maximum size is 96 MB. That means all the data, whatever the data you sent, will be split across each region, and the region will be spread across the multiple nodes. So the maximum region size is 96 MB, and each 96 MB of data act as an peer. That means each will have the regions will be replicated across the nodes. Each region will form a raft group. So so you might have heard of the raft consensus algorithm, right? This is the algorithm behind my MongoDB also. That is the similar architecture. So you can see here. So this is a TiKV, simple TiKV node, wherein you have a region 1 and region 2. Each region will have a start range as well as an end range. Okay. So you can see here. This is just for an example. This becomes one region. These regions are automatically sharded and balanced across the available TiKV nodes. Okay, so each has a leader and a follower. Leader will be responsible for the reads and writes operation, and followers will be for the read operation. For example, if you want to get a read from a follower, you have to give the hint to the SQL layer to get the queries from the follower. So again, followers participate in the election. For example, in case of one fault, as I said, right, it is highly fault tolerant. In case of a node failure, so the next node, that means a follower immediately gets into an election for a voting process, and the new leader will be elected, and it will take over the traffic immediately. Yes, the replicas are already created. Come to the previous slide, I'll say. So the replica here is a 96 MB region. So region is a replica. For example, next slide. So this is how the replica is being created. For example, region 4, okay, it has the data from P to T, and the same region is being replicated. This is a leader. These are all the replicas. Okay. So it's like a shards. See, yes, replicas has already been replicated to the other nodes. That means this shard of data, this region has a shard of data. That means range of data. Say, come to the previous slide. So here you can see. So this is a region. This is a piece of data. This data is being replicated to the other nodes as replicas. So the read quorum. It's not local. By default, it's a quorum. So for example, it see. So yes. So it can be both local quorum as well as a DC, means region based quorum. For that we have a concept called labels. So you call it as in Cassandra you have snitch, right? Similar to that, this TiDB supports a label, wherein in the label you can define what are the nodes to acknowledge the writes. For example, in the other region you might have 3 or 4 nodes, so that the transmission from a val based is higher, right? For example, in the other region you might get an one acknowledgement. That means that entire region gets full. That means it's not a local, both it supports both local quorum as well as by default it's a local quorum. Yes. So it has additional keywords. Entire MySQL syntax. And see, for example, this forms a single wrap group, multiple of which forms a multi-wrap design. For example, if this node goes down, so other node will immediately take over with respect to the region, and also your data is highly available. So next. Sorry, it's not possible. It's a sharded database. Okay, so coming back to the important point, this is a PD. So PD is nothing but a placement driver. This sits on top of the cluster. This orchestrate everything. This PD will have the global view of the cluster. That means this is the only part of the TiDB that touches both the SQL layer as well as the storage layer. This PD is highly available by default. It has a wrapped algorithm. For example, it itself communicates within them. For example, if one of the PD node goes down, other will automatically take back. So what are the functionalities of placement driver? The placement driver holds the metadata. So at which node has which region, that means location of the particular region. And also with respect to the distributed computing, the important thing is the timestamp allocation, that means TSO. When an incoming transaction comes through via the SQL layer, that is that is TiDB layer, the TiDB contacts the placement driver and gets a range of TSO for this particular transaction ID plus a TSO, and from the TSO it sends back and gets that. So the via TSO and the transaction ID, the isolation is being handled at the TiDB. And other important function of the placement driver is load balancing. So for example, you might have a data region, or for a particular node it can create a hotspot due to the frequent accessing of the data. For example, you might have a reason data that is being held in particular node, that means say node 3 or node 2. That node might be highly under pressure, that means the utilization might be high here. So PD continuously monitors the underlying data, that means the disk utilization, the data utilization, as well as the load of the server. And if a particular node is highly being used, it switches a leader node to the that is a leader role to the other node to take over the load balancing. It's it, so it's not about a single node. For example, if you deploy a TiDB cluster, right, you should minimalistically have a 3 nodes. Okay, and you can also add a number of node based upon the use case. For the hotspot problem, right, it is solved to extent, it cannot be solved at all, means at a max it cannot hold. So as you said, if there is a 10% load being handled and 90% load being handled the other, it switches, it tries to switches, means it is not immediate. For example, if there is an immediate switchover, right, the leader role switches, obviously the connection and also the queries which is being fired, right, that has to be switched. So it take a means it carefully switches the leader role without affecting the production. That means you does not see any implications because of this leader role switch in the application. And also another important thing is, like, for example, as I said, as the region size is 96 MB, beyond which doesn't grows when, and also it monitors the regions accordingly. Whenever a region grows beyond 96 MB, that means beyond the allocated size of the region split happens. That means it internally splits the region and distribute it to the other available nodes. And also according to set, it does not split immediately after the 96 MB. It will wait till a range, for example till 120 MB, it is the highest limit. So post 120 MB, if a region goes, it just splits into 2 region and distribute among them. And also vice versa, when a region, for example, if you do some deletes and compaction happens, when the region decreases in size, for example, if it goes beyond 20 MB, it will be merged to the nearby region, that is a shorter region, and placed as a single region. Okay, and also it does lot of scheduling by collecting the informations. For example, so when to do this leader split, and when to have this scheduling activities is being done by the placement driver. And also the placement driver powers a dashboard. That means a monitoring dashboard is being powered by the placement driver, because this is a place where you get the whole information about the cluster. So again, this is TiFlash. So this is an optional one. So this is an analytical store which is inbuilt with respect to the TiDB. For example, when you have a MySQL, you have to build a separate pipeline to get to the Redshift or via the bin logs. So this is like an automated pipeline. When you enable the TiFlash, it is not like when you just add a TiFlash node, you get all the entire data being populated to the TiFlash. It's not like that. You can control the number of tables as well as the database to be replicated to the TiFlash. So this TiFlash is being asynchronous in nature. That means it gets the data from the TiKV node. They follow a wrapped learner algorithm to get the data. And also there is a feature called intelligent engine selection feature that is available with the SQL layer node. For example, you have both, that is a TiKV as well as the TiFlash in the cluster. When a query comes for aggregation, for example via the SQL layer, the SQL layer passes the query. Is it aggregation? It directly sends to the TiFlash, not to the TiKV node. So this is the intelligent engine selection which is inbuilt with respect to the SQL layer. And also you can give a hint to use a TiFlash. For example, you have a particular query that needs to be go to the TiFlash, not TiKV. You can hint the queries and you can forward it directly to the TiFlash. And this analytical storage is built on top of ClickHouse, so which is an open source columnar storage. So this is in par to that, and this is optimized for aggregation, joins and things. And this is also MPP, that means multiple parallel processing is available. And this TiFlash also has a co-processor. This is also highly available in nature. That means this also has the regions, replicas is available. And also with the TiFlash, you can also define the replication strategy. Means how you intend to replicate it. It's a 2 replica or a 3 replica based upon the node which you create. Okay. So this is a complete detailed architecture. So you have your SQL layer, that is TiDB. So you have your key valued storage layer, that is TiKV. You have the regions forming a wrapped group, and also you have the TiFlash. So this is also this follows an, as I said, this follows an wrapped learner algorithm to get the data. And this also the DDL means, for example, you do a alter with respect to the TiKV node. This is also being traversed to the TiFlash node, because this TiFlash gets the information of this DDL activity from the PD and applies on its own. Okay, so as I said, it supports a native sharding. So the data which you put into the TiDB is automatically sharded and distributed. So how this sharding works is, so it is based upon a shard key. So shard key is basically a combination of primary key plus table ID. So they call it as a global key with respect to the TiDB. For non-integer means, for example, you have a table with primary key with int. It is directly takes an integer plus a table ID. Table ID is generated. And for a non-int primary key, for example, you have varchar, an invisible int primary key is being generated by the TiDB itself, and it is used for the distribution. So next slide we'll see. So for example, this is a conversion from relational to key value pair. So you have a relational data wherein one means this is a relational, and this is how the table ID is being generated. When, for example, for table T24 row 1, so this becomes a globally identifiable value within the cluster. Next slide. Okay. So this becomes your key and the remaining becomes your value, and immediately post this, the region split happens. So this is being split across the region 1 and region 2 and distributed across the nodes. Okay, so these are some of the use cases across the world where TiDB is being used. For example, let's take the example of e-commerce platform. Flipkart is being highly using the TiDB. You have super coins, right? For example, you might have shopped and you might have the super coins. This super coin is completely powered by TiDB cluster. And also, this is an IoT service wherein they are handling more than 1.5 million TPS per second with a TiDB cluster. And delivery is into the logistics, it is suited for it. And Razorpay is into the fintech and the payment gateway. BookMyShow is also using TiDB. And PayPay is another payment company from Japan. And also you can see a lot of customer stories with respect to the TiDB in this link. Okay, so again coming back to the production readiness. So as we have seen a lot of use cases, they are all being used in the production. So TiDB is completely production ready. So these are some of the checks you do before the production readiness or you move towards your workload to the production. And as I said, it is completely wire compatible with 5.7, and also 5.7 is coming to end of life. You can leverage TiDB with respect to that. And this again coming back to the UTF-8 MB4 is a default character with respect to TiDB, and some of the collation, for example, you might have in MySQL, you have Latin, Swedish one. Those some collations are not supported. It's only a binary collation is supported. And again, before moving your workload completely, profile your workload in staging or POC environment. Again, CDC with TA binlock means binlock support is available with TiDB. That means you can have a replica from TiDB, you can replicate back to MySQL. And monitoring integration, as I said, the PD as a Grafana dashboard and Prometheus alerting is available. And it also supports, there is a feature backup, that is they call it as BR. It support both physical backup with incremental and full backup, and also you can use a logical backup tool such as MyDumper on top of this also. Okay. And when it comes to limitation, the objects, so for example, in MySQL you have the stored procedures, triggers, foreign keys, and those object support is limited with respect to TiDB. Stored procedure is not supported in the upcoming version, like the current version is 7.1. So from the upcoming version they have plans to support for triggers, but it is not officially released. And the full text spatial index and column level privileges are not supported with respect to TiDB. And there is lot of many other features which is not supported. You just read through the limitation. Those are all not, these are the major limitations with respect to TiDB. Thank you. Sorry. The service discovery works via the PD. For example, when you add a node, or when you import the data, that happens via the PD. When you add a new node, that node get attached to the PD, that means discovered via PD, and the PD schedules the balancing. For example, you have added a fifth node, so that fifth node will get the data scheduled by the placement driver. Sorry,
what would be the main
so it has a YAML file and a configuration files.
So that should be on all the 5 nodes.
Yes, not on all the 5 nodes, on the PD. That is a placement driver, the centralized place, right? So that is where your node distribution and scheduling happens.
So will there be one placement driver, or each node will have separate placement?
No, see, the placement driver is 3 node.
Okay.
So you can go back to the architecture.
Okay, so there will be 3 placement driver, and there will be other the DB will be other
Separate.
than that. Okay.
It's a decoupled architecture.
Okay, so it will act as a conscious.
Yes,
so
orchestrator.
Okay. Thanks.
See, the adding a node is online. Means, for example, you can add your nodes, and it automatically distributes the data to the node and balance it. It depends upon your data and network throughput and your okay.
Here segregation is not there for read and write replica, so we are using cockroach, and cockroach it seems like the architecture it's similar to cockroach. So whenever there is a huge some read queries, it may be impact your entire application. So is there any solution for that?
So with the read queries, as I said, right, you can use the followers. Means it is not mentioned, it's not by default the leader role. That means it has 2 roles, that is a leader and the follower. So leader tend to take all the by default reads and the write operation. And when you say that you have a lot of read queries, right, you can give a hint to your in the queries to use the followers. That means the followers will be distributed across all the nodes, so by which you can leverage the read scaling. Okay. Uh, it is highly consistent. That means it has an ACID compliance. So to answer your question, so it basically uses two logs, two rafts. Okay, so for the it writes to the log, okay, and it commits a transaction. From the log it gets syncs to the another raft, that is the TiKV raft, and syncs there. So that is a detailed architecture. I just covered a basic.
Like if someone is running a select star or select count star, it will impact in entire nodes, right? If they're big table, so in that case how it will.
So that's why I gave example. For example, if you run a select count of star, so data is being spread across all the nodes.
Right.
For example, node 1, node 2, node 3. So now the SQL layer, right? So it parses it and it gets the metadata information from the PD. That means where your data actually exists, and it sends a query parallelly to all the available nodes. If you run a select count of star, that is the basic thing. So it sends to all the available nodes. From the nodes, for example, each will have a coprocessor. So the coprocessor will compute the data. For example, it has 1 to 30 data, 30, and it will have 30, 30, 30. So the coprocessor will send data back to the TiDB, and the TiDB is just to collate. That means it add all the 30 and give you the result set back. So if you run anywhere, if you run a count of star, right, it will be spreading across.
Okay. During that time, if some
See, for example, if you have a TiFlash node, so TiFlash is basically for the analytical workload. So if you run a select count of star, so it has a feature called intelligent engine selection. So when you run a select count of star, it understands that this is a aggregation query or analytical query. It directly passes the query to the TiFlash to get you that count of star.
Okay. So means real time data we will get from there.
Real time data will get from there. So it is asynchronous. So the analytic count might lag, but not to a greater extent, to a smaller extent.
Okay.
For example, and also one more thing. For example, when there's a live replication ongoing, if this TiFlash node goes down, for example, in certain cases, this does not affect your cluster. So cluster will continue to run, and when it comes back on it gets incremental data. So your analytical performance will get impacted, not your production workload will not get impacted. See, for example, if you are using a mix of workload, for example, mix of both read and analytical workload in the same, so your analytical workload might get impacted, or if with the SQL means the engine selection mode, if it is being used on the TiFlash, right, that might get populated back to the TiKV. In that time, you might see some latencies because of the performance. So this is based upon LSM tree.
Right. So this is the key value
Storage.
So I think the change in the underlying storage model that would impact the performance of some queries. Right. Some queries might be easier to do in the traditional model. Some might be faster and easier to do here. Right. Can you give a like a summary of what queries are difficult to do in the KV model versus what becomes easier?
So KV model is basically for your transactional workload. Okay, so for example, it is similar to MySQL. If I might have worked with B-tree, right? Similar to MySQL, the transaction workload will be served but better with respect to the TiKV module, and some of the read performance might get hindered. Actually, this is a known thing with respect to the RocksDB. Okay, so writes are pretty heavy or pretty faster with respect to it handles the writes well, and read, when you compare with MySQL, right, there might be little latencies, but the use case and the means the load testing studies does not show that.
I would say it will perform well for a separately workload rather than update intensive workload. Every update basically creates a child version of the row, and end of the day it will go through a compaction.
Yes, compaction.
And when compaction hits, your cluster will start starting.
No. So again, this is
that's the case of LSM.
LSM tree, exactly. And also this RocksDB is being used. You can see Cassandra, Cockroach, everybody. The new SQL uses this, right?
And again, if you want a secondary index, that's also going to support you.
Secondary index is supported, but as you said, there will be a little penalty will be there on the use case.
The penalty will be substantial because you need to create a pivot table for the secondary index in
So
take C from the storage.
so that's the main reason. So you do your POC workload analysis and then you can move safely your workload. So because if you can see the customer data, right, so what we have read from the current use case and those things, we see a positive feedback for the TiDB for the use cases wise. It is again purely based upon the use case. So if I say me, right, for example, most of the customers, if you see the customer use case, so they have moved from Aurora to this node. For example, I said, right, there's a IoT based instance wherein they were using the time series data, the IoT data. They used Aurora, which was not scaling. If you read the use case, right, it is very much elaborate. It's open source. So and also they have their serverless as well as enterprise licensing there, but it's purely open source.
Yeah, I have a question. Can you talk about the secondary indexes you mentioned? I think I saw on the slide that all the data of a particular tuple, right, it's stored together as the value for a particular key. So is it possible to have an index on, let's say, some field, some column?
Sorry. Yeah, you can have it. It is based upon the primary key. It is built on top of the primary key. So that is your key value pair. So as Harish also said, right, the same thing. Any other questions?